It's consistent with my claim that there's really nothing new. Once you're done with chapter 8, there's not a whole lot that's new, at least up to a certain point. So, and I mentioned that multiple times, and it's true here because you're thinking, hey, chapter 13 is about gravity. And haven't we learned about gravity? We learned that the weight force, sometimes expressed as F subscript G, we learned that weight is mg. I mean, we all know weight equals mg. And we even dealt with gravitational potential energy equals mgh, some height with respect to a baseline. All of this was true, and all of this assumed the object was on or near the Earth's surface. So now we generalize that. We use Newton's law of universal gravitation to basically figure out what's going on between any two objects. For example, a grain of sand on the planet Mars exerts a gravitational attraction to a grain of sand sitting on Pluto. Every object in the universe attracts every other object in the universe. So there's this completely universal gravitational attraction. And then, not to go off on this sidebar, then if that's true, which it is, why is the universe expanding? So stay tuned for dark energy and dark matter conversations. But for now, we are secure in the statement that every object in the universe attracts every other object in the universe. And we're not going to limit ourselves to an object on or near the Earth's surface. So this is where our very first inverse square law comes into play. This is Newton's law of universal gravitation. G m1 m2 over r12 squared. This is at the heart of chapter 13. This is one of the four fundamental forces in nature, the four primary forces in nature. You have the gravitational force, you have the strong force. The strong force is what keeps atomic nuclei together. You have the weak force, which explains why sometimes atomic nuclei decay and spit out radioactive particles. And then you have the electromagnetic force. So really, chapter 13 is the first chapter that's squarely focused on one of the fundamental forces in nature. Every force in nature is one of these forces or a combination of these forces. So for example, we know about the friction force. F sub n is the normal force. The normal force is actually a combination of the gravitational force and the electromagnetic force. So, and it goes on. So we're going to do our very first chapter 13 problem. And we're going to use an approach that is ripped right from exam 3. Remember on exam 3, there was a problem that said, hey, you have, you need to do a there's a collision problem. You had these three objects flying in from their initial positions, and they collide at the origin, and then they stick together and they go off in the x direction. And I said, suggestion, use two XY momentum tables as part of your solution. I changed it to suggestion. I changed it from mandatory to suggestion. I'm thinking I really should have made that mandatory. I think that would have helped, because the whole idea behind breaking things down into an XY table, the whole idea behind breaking things down into components, decomposing things into an X component and a Y component, there's a double benefit. It means you have a higher probability of getting the right answer, and I have an easier time grading it. So if one of those wasn't true, then I could see it. An argument could be made that, well, maybe it's not that important. But because both of those are true, I probably should have made that mandatory. And if you see something like this on exam 4, I probably will say mandatory. You have to use this method just because it's going to result in higher exam. It's going to result in higher exam scores, and it's going to make it easier for me to grade your work. And that has to be a consideration. This is true when on the job, you get your first job for whatever company you work for, you have to do work that's easily digested. So gradability, readability, et cetera, all that's important. So here's what's going on. We have 3 objects, and I know that each one of these objects will mutually attract the other 3. So, but what's going on here is they're basically saying, hey, if you lay out these 3 objects the way you see here, what is the value of mass M such that the net force on this object in the middle is 0? That's the first question. So you know what I'm going to do? I'm just going to do my own numbering system. I just like to use just my own indexing. So if that's M4, okay, that's M4. I'm just going to call this is M1. This is M2. I'm not changing anything. I'm just using my own naming system. That's M4. I'll call this M3. And again, this is M4. Okay, just writing it bigger and clear. All right, so it's saying, what is the value of M3 such that the net forces acting on M4 are 0? Okay, so this is, here's chapter 13. Chapter 13, sort of a key part of chapter 13 is force analysis. And then another key part is energy analysis. And then another part is orbital analysis. Pretty cool. Orbital analysis, like satellites or moons or neutron stars, and orbital analysis. So those are the 3 macroscopic categories for chapter 13. So the first 2 problems today, I think, are focused on just force analysis. Force analysis means free body diagram. So let's go ahead and add some forces here. This central object, M4, is going to feel an attractive force like that. Between M3 and M4, there is an attractive force. We don't care. I don't care what's going on. I don't care what M3 is experiencing. I only care about what M4 is experiencing. And then there's a gravitational attraction force between M4 and M1. And last but not least, there. Okay. So let's use this labeling scheme. I've blurted this up before, but let's do the on what from what. Let's use that as a convention. The on what from what convention. So this would be right here. This would be the F. This is the force on what? On 4 from 3. Down here, this is the force on what? On 4. This is the force on 4 from 2. And this is the force on 4 from 1. So on what? From what? Gravity is always attractive. Now, if we wanted to, you could say, well, let's just take a look at M3 just for the sake of discussion. There is actually a force exerted on M3, which I could draw like that. And the force exerted on M3 is a gravitational attraction force. And I would label this the F on 3 from 4. But I don't care about M3. M1, M2, and M3, all of these, all of these charges are exerting a gravitational attraction force on every other charge. But I'm examining M4 because it's M4 that is sitting in the center of that triangle and is experiencing no net force. Okay, so I'm going to get rid of that since I will say this. I know one thing. I can say the magnitude of F3.4 equals the magnitude of F4.3. This is Newton's third law. So it's basically saying M3 is saying, hey, M4, if you're pulling me towards you with that green force, I'm going to pull you towards me with that brown force. So Newton's third law applies just like always. This is just another force in our toolbox. Okay, and You could look at this. You could look at this problem and you can see a lot of very obvious symmetry. It's an equilateral triangle. M1 and M2 are equal to each other. I mean, to be honest, you guys, I could probably do this in my head, and you could probably do this in your head without writing much down at all and get the answer pretty quick. However, I'm going to take the harder path because it's almost always better to take the harder path. And I'm going to take the harder path here because what if on exam 4, I have something like this? What if I have a coordinate system? So what if I just have an XY coordinate system and I don't have anything quite so nice and neatly laid out? What if I had a particle there and then a particle here and then a particle there? And all of these were different. Everything was different. Nothing was symmetrical, just completely asymmetrical and completely unique in terms of values. So that's why I want to do the XY force table approach. Okay, so which hopefully, well, I know who did and who did not use this approach for the momentum. And I'll say it again. The advantage here is if you use this XY force table approach, your chances of getting the correct answer go up. My ability to grade your work efficiently goes way up. Vector, name, X, Y. So this is us just decomposing things into components and then dealing with them that way. Seems like a logical thing to do. All right. Okay. I'm going to do let me overlay a coordinate system. So I'm just going to superimpose this coordinate system. Okay. All right. And I'm going to specify angles. And if you remember, one of the specifications is, or one of the conventions is specify all angles as CCW with respect to plus X. So all angles, specify all angles as going counterclockwise with respect to plus X axis. I think I stated that on the first day, and that's in your first stack of green sheets. So, all right, having said that, let's specify all angles as going counterclockwise with respect to the plus X axis. This will be theta. I'll call this theta 41. Theta 41 is theta 41. That's theta 41. Fine. Because this is the plus X axis and I'm going counterclockwise. Here's theta 42. Like that. Theta 42. And then here's theta 43. Done. Okay, so very consistent. This is what I call a best practice. This is whenever you have to decompose stuff or whenever you need to decompose stuff, which you want to do often to make the analysis easier, just use consistency and rational approach. And hopefully if you guys see, and this actually happens, if you see any opportunity to change what I'm doing so that it's even more efficient or even more rational, let me know. And I've lost track of the number of times I've accommodated those suggestions. All right, so let's just say right here, what's theta 41? Theta 41, I'm going to look at theta 41, and I can see it's going to be 180 degrees. And now I just have to get smart. I got to get, so theta 41 is 180 degrees plus whatever this angle is right here. So what is that angle? Well, this is where some simplicity can get used. This is an isosceles triangle, or no, equilateral. It's an equilateral triangle. So if it's an equilateral triangle, that means this is 60 degrees, which means this angle is 30 degrees. This angle is 30 degrees. This is 90 degrees. This must be 60. must be 30. Anyway, that's how I do it. That, and you know, I'm kind of, let me just repeat what I said in case you're following, but I'm sort of assuming you guys can kind of be autonomous in terms of figuring out these angles. But let me just go through that one more time, because it's I always take this sort of, you know, just sort of what if approach. What if well, I need to find that red angle. That red angle, I know well, and you could say, well, you know it's 30 degrees, but this was my thinking is my thinking was, well, this purple angle is 60 degrees. This angle is bisected, so that's a 30-degree angle. That's a 30-degree angle. I know that's 90. 30 plus 90 means this must be 60, and that must be 30. And you guys probably saw, well, of course that's 30 degrees, but I wasn't quite seeing it super obviously like that, which is why I just went through maybe another meandering approach. But 180 degrees plus 30 degrees equals 210 degrees. That's theta 41. What's theta 42? Theta 42 is going to be 270 degrees. I'm going counterclockwise with respect to the x-axis. And same sort of little dialogue. Well, that's 60 degrees, which means that's 30. That's 30 degrees. Well, and if this is 30, that's 90. This is 60. So there, that's the answer. That's 60. So it's 270 plus 60 equals 330. And theta 41 equals theta 43, sorry, theta 43 equals 90 degrees straight up. Okay, so let me get this out of the way a little bit. All right. The other thing that I think I'll do, as long as I'm here, I'm going to look at what are the distances, because all we're doing is we're applying Newton's law of universal gravitation, which is F equals G m1 m2 over the distance between 1 and 2 squared. So I'm going to talk about distances. So let me clear a bunch of this stuff. Maybe I'll clear, well, I'm going to leave it. Here is particle m1. So m1 is, here's m1. M1 is right there. That's m1. What's the distance between m1 and m4? M4 is right here. I don't know. But I do know the distance between m1 and m4 is the same as the distance between m2 and m4 is the same as the distance between m3, which is here, and m4, and they're all the same. So I guess I have to use that low-hanging fruit, because I'm thinking, what if those distances weren't equal? It would force you just to keep committing to this approach. So I'm going to say the distance between, the distance between 4 and 1 equals the distance between 4 and 2, which is the same as the distance between 4 and 3. Why do I know that? Equilateral triangle with that gray dot M4 sitting right in the middle. So let's just call it R. All right. So that is gonna make for some easy calculations. All right, so let's go through and do the table. It's table time. Here's vector F41. F41 is down here. It's like that. That's F41. Here's the angle. This is theta 41. Okay, so what's the name here? The name F on 4 from 1. Here's the X component. Follow the subscripts. G, M1, follow the subscripts. G, M4, F41 means you do M4 and then M1. Cosine captures the X component. And it's an inverse square law, so this would be R squared. Remember, R41 equals R42 equals R43 equals R. Same for Y. This is going to be G M4 M1 all over R squared, but I'm taking the sine. Sine is what I use to capture that Y component, and then repeat. Here's F42. F42 is this vector going like that. And then my going counterclockwise with respect to the plus X axis. This is theta 42. So here's Newton's second law, or Newton's law of universal gravitation, G. Let me fix this. It's not F2, it's F42. Is G M4, M2, all over R40, R squared. And then cosine captures the X component, and then rinse and repeat for the Y component. G M4 M2 all over R42, and R42 just equals R sine theta 42. And last but not least, F43, that vector is going straight up, and here's the angle. Counterclockwise with respect to the positive x-axis. This is theta 43. G M4 M3. I'm just, because it's F43, I'm going to do G M4 M3 just to be, again, very clear. R43 is the same as R, so let's just call it R squared. Cosine theta 43, G M4 M3 all over R squared sine of theta 43. And you know what? All of these vectors, when you add up all of these vectors, you get the net force acting on particle 4, which is 0. 0 for X and 0 for Y. Because again, the question said, what's going on? What is the value of M3 if the force, the net force acting on particle 4 is 0? So all I'm doing is I'm saying, hey, take this X component plus add this X component plus this X component plus this X component, and it equals that. Same over here. I have this Y component plus that Y component plus that Y component equals 0. So this is standard. This is just a standard vector table applied now to force. Again, on exam 3, you ideally would have used this approach for momentum. For all of the aforementioned reasons, I'm just going to do a little bit of cleanup to make a table out of this. Not that you're not seeing it, but all right. So I would just say, well, okay, here's the table. Here's the table I have. All right, I have a table of X values and a table of Y values. And let me just, like that, good enough. Okay. Okay, so where's my dollar sign? My dollar sign is M3. What is the value of mass? They call it capital letter M. I'm calling it M3. So here's my dollar sign. My dollar sign, there is my dollar sign. And here's my dollar sign. So I guess I'm just going to go through and add up. Again, so much of problem solving is just cough up enough equations so that you can solve for the variable you're looking for. So I'm going to add up. Let's add up X column. So if I add up everything in the X column, hopefully that will yield my M3 dollar sign. So ready, G M4 M1 all over R squared cosine of theta 41. Yep. Plus, I'm just adding the x components, G M4 M2 all over R squared cosine theta 42 captures that x component. And then my third x component is going to be G M4 M3 all over R43, but R43 is the same as R41 and R42, and we're just calling it R squared cosine of theta 43. And whatever all of that adds up to be, it adds up to be equal to 0. Because all I'm doing is I'm just going down this column. I'm just saying, hey, whatever. I'm just adding up all of these components. Okay, so now there's some low-hanging fruit. If I can divide through, if I divide through by big G, it goes away. Big G, I'm dividing both sides by big G. I'm multiplying both sides by R squared. I'm dividing both sides by M4. So look how easy this got. Look how it became so easy, because right now I'm left with this. After canceling my low-hanging fruit, I have M1 cosine theta 41 plus M2 cosine theta 42 plus M3. There's my dollar sign, cosine 43 degrees equals 0. Looks pretty easy because here's a problem. Theta 43 is 90 degrees. So this whole thing equals 0. So this is where I have to write, stuck. I'm stuck. So number 3 is not an invalid equation. It's just, it's not sufficient. I can't get M3 from that. So let's look at the Y data. Look at Y column. All right, so I'm going to do the same thing. I'm just going to take all of these components, add them all together. They equal 0. And let's see. And if this doesn't work, if I get stuck, then I keep going. You can say, well, okay, what else can I tap into? But if I add up the Y column, G, M4, M1, all over R41 squared, sine of theta 41, plus, just go down the column, G, M4, M2, all over R42 squared, sine of theta 42. Last but not least, G M4 M3 all over R43 squared times sine of theta 43. And all of that equals 0. So low-hanging fruit. Let's divide through by G. Let's divide through by M4. Let's multiply by R squared. So that leaves me with M1 sine theta 41 plus M2 sine of theta 42 plus M3 sine of theta 43. And theta 43 is equal to 90, so sine of 90 equals 1. But maybe at this point, let's see. More low-hanging fruit. It turns out that M1 equals M2. So I'm just going to replace M1 and M2. I'm just going to call it letter M. So I'm going back to like their initial spec. So this is M. This is M. So let's just do the sanity check here. Do I know the value of M? Yes. Do I know the value of I know the value of all these angles. Here's your dollar sign. Let's get the answer for M3. Okay, time to calculator. All right, M3. So is that a coincidence that M3 has the same value as M1 and M2? Maybe, maybe not. And again, you probably could have solved this using all of the simplicities and simplifications, but it wouldn't be like that. You'd have to use this method on exam 4. But part B says, what's the magnitude on that M4 if we double M4, what happens to the net gravitational force on M4? So number 8. Look at number 6. Look at number 6. Number 6 basically says, what is, if we double the value of M4, what is the magnitude of the net gravitational force on the central sphere? Am I reading that right? M4 is the central sphere. Okay, so I'll say this. If M4 is doubled, the net force, the F net on 4 remains equal to 0. I can say that because if I look at my number 6, if I look at equation number 6 here, M4 is nowhere to be found. So I can put anything, I can put a mass of any value in the middle of that triangle. And no matter what is sitting in the middle of that triangle, it's going to feel 0 net force. I'm just saying, look at equation 6 here. M4 is nowhere to be found. It got canceled out up here. So once again, I could put a ping pong ball or a sphere of gold. It doesn't matter. It will experience no net force, which is kind of a common theme in this chapter. You'll see that the object that we're analyzing actually doesn't play a role. We're going to figure out what needs to be, calculated, but the object itself is kind of interchangeable. All right, so that's our first force analysis problem using the XY force table. Now and when you go back, you guys, I don't know if you're doing this, but I would highly recommend going back and rewatching these Tuesday Zoom sessions. I don't know, I think this is probably a bad assumption. I was sort of assuming that you guys always go back and rewatch these lecture videos. I could see if you take hyper meticulous notes, then I could see you saying, I don't need to do that. But I don't know. That's just a habit I kind of learned back in my early 70s. No, back in, I learned that kind of late, like, hey, rewatch the material. Let's do the next quiz, chapter 13 quiz. We are doing the next quiz 2. Let me get that ready. If it's not already. Chapter 13, quiz 2. It's now 138. You should now see it right now if you refresh. Chapter 13, quiz 2 is problem 12, which is a homework problem. Okay. And now a quiz problem. This is more force analysis. So this is another force analysis situation, which is sort of one of the three basic subtopics of this chapter. In this figure, particle A is fixed in place. So basically, I have particle A right here, which is glued into place. All right. I know the distance between A and B. B is sitting there at the origin, and I know that distance. It's, for me, particle A is 0.3 meters to the left of particle B. There's a third particle, particle C, which is not shown, but particle C can be moved along the x-axis between B and infinity. So here's particle C, somewhere to the right of B and to the left of infinity. So this is particle C. We have a graph. We have a graph showing the net gravitational force acting on B due to particles A and C as a function of C's position. All right, so interesting, huh? I'm going to do standard graphical analysis. You squeeze everything you can out of this graph. And I'm thinking, well, here's some obvious points. This seems to be an obvious point. This orange dot is definitely eye-catching because that's where this curve crosses the y equals 0 axis. That's where I have no net force on particle C. And then it actually gives me an asymptote, which is another thing you look at. You look at maxima, minima, slopes, area under curve, x-intercepts, y-intercepts, crispy intersection points. Standard cast of characters in terms of squeezing out every bit of good stuff from the graph. This is my asymptote right here. And they're saying, basically the question is saying, when particle C goes off to infinity, this is the net force acting on particle B. Yes. All right. So this asymptote is negative 4.86 times 10 to the minus 10th newtons as this goes off to infinity. All right. So maybe I need to get some more points. Like maybe should I maybe consider, I mean, this seems to be like maybe a contending point. That looks like kind of a halfway mark. So maybe that will be good. All right. There. Okay, so I'm just going to proceed. This is force analysis because when you read this problem, you have to know that you are dealing with a force analysis situation. So I'm going to do my free body diagram. I have the force on B due to A going to the left, and then I have the force. Let me draw that again. Okay, and then I have the force on B from C going to the right. Let's label that. This is the force on what? From what? This is the force on B from C. This is the force on what? From what? On B from A. Okay. So I can say the following. Number one, when particle C, when the mass, which I'll just write as M subscript C is just referring to mass C. When M subscript C is at x equal, for me, 0.4. I'm looking at this number. When particle C is at x equals 0.4 meters, the net force acting on particle B, F net x on particle B, yes. I'm just reading the question to make sure I'm just reading the question a bunch of times to make sure I'm remembering what this is a graph of, which means I need to read it a whole bunch of times, equals 0. Okay, so let's do this. All right, so F net B equals 0, and is also comprised of negative FBA. I'm just looking at my vector drawing. Here's negative FBA, and then I have FBC going to the right. So going to the right means plus, not minus, FBC. There it is. So let's keep going with this. And I'm hoping my dollar sign lives in here somewhere, because we're basically after the mass of particle A and C. We know what it is for B. So I guess I could say FBA. Here's FBA. And I'll just say this means FBA, which is going to the left, must equal FBC, which is going to the right. You probably can see that right away. But here's FBA. Ready? Follow the subscripts. GMB, MA, because again, it's FBA, and I'm just saying, okay, I'm going to stay committed to this order. It's B and then A. So GMB, MA, all over the distance between those, and I'll just say RBA. It's RBA is the distance between B and A. That has to be squared. That needs to equal FBC. GMB, MC, all over the distance between B and C squared. Low-hanging fruit. Let's divide both sides by G. Let's divide both sides by MB. So what am I left with? Well, my dollar signs are in there at least. So I'm going to have MA all over the distance between B and A, which is right here. The distance between B and A, this distance between particle B and particle A, for me, is given as negative 0.3. So I'll just square negative 0.3. Negative 0.3 meters squared equals MC all over RBC. And here's the distance between B and C at this particular location, which is, this is the location I'm tapping into. I'm tapping into the situation when particle C is located at 0.4 meters, plus 0.4 meters. That's the difference between B and C that I'm exploiting right now. So this would be 0.4 meters squared. So you know what I can get out of this? I can get MAMC. I can get MA equals 3.75. So that's not my answer. That's not my answer. I'm thinking it might come in handy, but that's not my answer. So now what do I do? So this is, I'm thinking, it's good to know, but now what? Now what? The now what is look at the asymptotic case. So I'm going to look at what's happening. Look at situation. Look at the situation when particle C, which is that movable particle, that object, when MC goes off to infinity. Okay, so let's just do the same thing. When particle C moves off to infinity, so even here, I'll just say particle C is now located at infinity. And those are my same Those are my same force vectors. So I'm going to repeat a lot of this. Well, I've repeated all I'm going to repeat. When particle C is at infinity, the net force acting on B is not equal to 0. It's actually equal. It actually equals negative 4.86 times 10 to the minus 10th newtons. It equals that asymptotic value. That's the net force on particle B when C has wandered off to infinity. Yes. Equals negative FBA, so negative G MB MA all over the distance between B and A squared. So again, I'm just using my free body diagram. I'm saying I've got this leftward force. I got the leftward gravitational force pulling particle B left toward A. And then I have this rightward gravitational force acting on particle B, pulling particle B towards C. That's why this gets the negative, because that's FBA plus G MB MC all over RBC squared. This becomes now negative 4.86 times 10 to the minus 10th newtons equals, okay, now what? I'm going to pull out a common factor, equals GMB. I'm going to pull out that common factor, GMB times, maybe I don't want to do that. I'm not going to quite yet pull out the common factor. Equals minus GMB. And then, you know what I'm going to do? I'm going to replace MA. MA, according to step 4, MA can be replaced with 0.75 MC, which is a dollar sign. All of this over the distance between B and A right here, squared. The distance between B and A is this distance as previously indicated. For me, this is negative 0.3 meters. So this would be negative 0.3 meters squared plus GMB. And I'm not bothered by that because I know the value of G and I know the value of B. And here's MC again. I'm not bothered by that because that's my dollar sign. What's the distance between B and C? It's infinity. Because I am keying on this asymptotic case when object C is relocated off to infinity. This whole thing disappears. So now you know what you can do. You can solve for MC. All right, so let's see. Oh, here's G. G. This is definitely in the Hall of Fame. In our universe, there's a small handful of truly absolute constants. Here's one of them. This is the first absolute universal constant that we've had in this course. And it's equal to 6.67 times 10 to the minus 11th Newton meter squared all over kilogram squared. So again, this is our first Hall of Fame. This is our first opportunity to meet a Hall of Fame universal constant. There's more, but there's not a lot more. And there's more digits. It's like 6.67384, goes on and on and on and on. But I believe Wiley Plus just rounds it to 6.67. Okay, so do you know the value of G? You do now. Do you know the value of MB? Yes, for me, it's 3 kilograms. So solve for MC. And once you get MC, then get MA because of right here. Okay. So let's run those numbers. negative. Am I making a mistake somewhere? Negative 4.86. Okay. MC. MC.
Yeah, I think you have in step 4, I think your MA is wrong up there. Yours is set to 0.75. I think it should be 0.5625.
Where? In step
Step
4?
4. Yep. So if you multiply by 0.3 squared,
Oh, yeah,
yeah,
you're right. You're right.
yeah.
Yeah. It should be 9 divided by 16. You're right. Thank you. That's a good catch. That does solve the mystery.
By the way, wouldn't it technically be simpler to just solve for MA here?
I don't know. I don't know. It might be. 0.5625. Five, 625. 5625. Oh, come on. Well, all right. That is 0.5625, which means this is 0.5625. 0.5625. Okay, so negative 4.86 E minus 10 times 0.3 squared divided by 6.67 E to the minus 11 divided by 3 divided by 0.56. Okay, that's helpful. MB, so I just got MC. Yeah. Times 0.5625. Okay, good. Good. All right. So this is our second force analysis problem. My calculator says 0.2185907. All right. Good. That's our second force analysis problem. Using graphical analysis is very helpful. I try to steer toward graphical problems, and I always try to steer toward calculus problems just because there aren't that many of them, and calculus figures very prominently in your future. So let me get ready for quiz 3 since we're making good time. Chapter 13, quiz 3. So there's a deep dive for problem 14. There's a deep dive for problem 16. So our next step, quiz 3, should be problem 35. It's now almost 2 o'clock. All right, if you refresh, you are hopefully looking at this. This is our first energy analysis. Okay, so here's what's going on. I'm going to do a redraw, make it maybe a little bit bigger. I have 4 particles located at the corners of this square. So I'm going to, again, do my own square. Maybe here's the square, and then I'm going to do my own naming convention. So this is particle 1, 2, 3, 4. Okay. So this is M1, M2, and they all have the same mass. But again, this is just my habit. My habit is just to index everything because I'm always thinking, what if things weren't so simple? That's always in the back of my head. What if all of these masses were different? Okay, so so I have these 4 masses forming a square, each with an edge length of d. What is the change in the gravitational potential energy of the 4 particle system? So this expression right here was derived in detail in your green sheets and via the YouTube lecture video. The chapter 13 YouTube lecture video went into a lot of detail about how this is gravitational potential energy. And again, just to go back down memory lane, you might remember, we're all old enough to remember when gravitational potential energy was mgh. And again, this is true for on or near the Earth's surface. But we're just going to be generalized now. We're just going to say, hey, the Earth does not have to be around. This does not have to be limited to earthbound situations. This is the gravitational potential energy of 2 objects, in this case, MA and MB. So here, before we launch into this problem, let's get a feel for what this is really saying. Here's mass A. Here's mass B. What if I go ahead and I just glue, this is mass A, so this is a little sidebar conversation. And this is mass B. What if I basically glue mass A into place? So mass A is just motionless. What if I take mass B and I start moving mass B closer or further away? Here's a question I have. If I put mass B way over here, does this system, and the system I'm referring to is the system comprised of MA and MB. If MB is located far, far away, does that represent a greater amount of potential energy or a lesser amount of potential energy compared to MB, say, being super close right here? So this is how I think about it. If MB is located far, far away, and I let go of MB, MA is again taped into place. If I let go of MB, it's going to convert all of that potential energy into kinetic energy. So by the time MB approaches MA, there's a tremendous amount of kinetic energy. Versus what if MB started off right here? If MB starts off right here and I let go, I'm holding in place, but if I let go of MB, it's going to drift toward MA because of gravity's always attractive. MA is again taped into place. And it's going to convert. It will again convert gravitational potential energy into kinetic energy. But you see, I don't have as much. I don't have as much energy. I don't have as much gravitational potential energy starting out that I can convert into kinetic energy. So the farther away these 2 objects are, the greater the system potential energy. And here's the limiting case. What if MB is actually sitting out here at infinity? So this is MB parked at infinity. Imagine if I have MB out at infinity and I let go of mass B, it's going to have basically an infinite amount of kinetic energy by the time it hits MA. And that's our limiting case. That's our baseline. And all of this is in the green sheets. You're getting the cheap preview of the chapter 13 lecture video now, but just while it's right in front of us, here's our baseline. Remember, for EAM, you always had to talk about a baseline for gravitational potential energy. Now for universal gravity, we can just say the gravitational potential energy when two objects are located infinitely far apart equals 0. And then I think in the green sheets, it says 0 is the max amount of gravitational potential energy possible. 0 is a huge number. Everything else other than the case when these are infinitely far apart is actually less than 0. If you look at this expression, for gravitational potential energy, and I just took a little time out and went to Desmos, and I said, what does this look like graphically? Desmos, what's the sense? I'd say, y equals, it was minus g. So here's what it looks like. I'm going to say, well, you know what, for the sake of just getting a graphical view, I'm going to call G times MA times MB. Whatever that is, I'm going to say it equals to 1, just for the sake of simple graphing. So it's going to be negative 1 over X right here. Okay. So, and then I'll say for X greater than 0. For X greater than 0. This is it. You're looking at the gravitational potential energy curve for two objects separated by some positive distance. And you can see this goes asymptotically. This asymptotically approaches 0. So there. If we take the big view, it asymptotically approaches 0. And again, this is up close. It's basically all potential energy, all gravitational potential energy is always negative, except for the limiting case, except when you have this theoretical situation where the two objects are located infinitely far apart there. So that's different. I'm spending a lot of time on this for a reason. So now we can go back and solve this problem, because right now, this is energy state A. I'm going to call this energy state A. Energy state A is what's going on when I have these 4 objects located with this configuration or adhering to this configuration. Now, what happens when I move things together, when they move closer together? All right, so here's energy state B. Energy state B will be, it's still going to be a square, but now they've moved a lot closer together, like that. All right, so here's energy state B. I have the same 4 particles. Here's M1, here's M2, here's M3, here's M4, M1, M2, M3, M4. This, for energy state A, this was D, D, D. This, for me, it's I went from D equals 0.5 to D equals 0.1. So for me, I'm just going to write from right now, I'm just going to say this is D over 5. And this is D over 5. And these are squares. Okay, and this is energy state B. I know one thing. I can get a clue right now. I know that when I go from energy state A to energy state B, I know my gravitational potential energy has decreased for the exact same, based on the exact same conversation I had down here. if this is MA and this is MB right here, when MB is located far away and I let go, it's going to convert. It has all of that initial gravitational potential energy to convert into kinetic energy. So I can tell that the total system energy for state B is less than for state A. So I'm expecting a negative in my answer. So if I don't get, I'm expecting a diminishment of system potential energy when I go from state A to state B. If I don't get a negative, that's cause for concern. So here we go. Let's talk about the gravitational potential energy for state A. I'm going to leave off the G because we know we're talking about gravitational potential energy. So here's my total gravitational potential energy for state A. Ready? It's going to be, this is superposition, U12 plus U13 plus U14 plus U23 plus U24 plus U34. So this is called superposition, which basically says, hey, go ahead and just cluster things into pairs. So it's kind of like this whole decomposition approach. Let's break things up into components and then deal with all of the components once we've identified them. All right, so when I pair this up, let me just sanity check myself. I have some gravitational potential energy between M1 and M2. They do. There's some potential energy there. The potential to convert into kinetic energy and also to do work. All right, so I've taken care of M1 and M2. What about between M1 and M3? Okay, I counted for M1 and M3. There's U13. Here's the shared potential energy or the system potential energy between 1 and 4. I got it. So I'm just going after unique pairs. M2 and M3. I need to tally that up. I do. I have that. M2 and M4. Got it. 2 and 4. Right. And my last unique pair that I can see is 3 and 4. All right. So I think I've identified all the unique pairs. So here's the total amount of gravitational potential energy in this system for energy state A. It's going to equal, and I'm going to tap into this expression right here and follow the subscripts, minus G M1, M2, all over the distance between 1 and 2, plus, and then that minus sign, G M1, M3, all over R13, plus, this is just how I do it. I'm adding them all together, but there is this negative sign here. And the derivation will show you exactly where that comes from, but G minus G M1, M4 over R14 plus a minus G M2, M3 over the distance between 2 and 3 plus minus G M2, M4 over the distance between 2 and 4. And last but not least, plus minus G M3, M4 all over R34. Okay. That's the total amount of gravitational potential energy in energy state A. Let's do some simplification and let's add things together and simplify as much as possible. All of these masses are the same. So I'm just going to say if all of the masses are the same, this is going to be M squared. And this will be M squared. Okay, so M1 equals M2 equals M3 equals M4. And if you're asking, why didn't I just start out this way? Again, I'm always looking toward a more complicated, less simplifiable situation. But now that I've done that, I have no choice but to go ahead and go with what I know. All right, what is the distance between 1 and 2? This is D. What's the distance between 1 and 3? Well, if this is D and that's D, the distance between 1 and 3 is right here. And this will be D root 2. All right, so this is D root 2. What's the distance between 1 and 4? D. So this will get nicely simplified. What's the distance between 2 and 3? That's D. The distance between 2 and 4, that's root 2, or I guess I'm calling it D root 2. What's the distance between 3 and 4? That's D. All right, so here comes the much awaited simplification. The total system potential energy at A is going to be, I'm going to pull out common factors. I'm going to pull out a minus G M squared all over D. So if I pull out that common factor, minus G M squared over D, then this will be 1. Got to keep track. 1 plus 1 plus, nope. So this will be 1 plus 1 over root 2 plus 1 plus 1 plus 1 over root 2 plus 1. And I need to just sanity check myself here. I'm pulling out a common factor, minus G M squared over D, which means this better be 1. It is. This better be 1 over root 2. It is. This better be 1. This better be 1. Okay, I'm feeling good about this right now. This is the total system potential energy corresponding to state A. All right, let's do the same thing for state B. And maybe we can fast track this just a wee tiny bit. Okay, so, well, I don't know. It went pretty fast. And we're getting close to a break. So number 4, here's my total gravitational potential energy for energy state B. I'm just going to go through this just for reinforcement. I'm going to do superposition. It's U12 plus U13 plus U14 plus U23. So everything's the same. I could literally copy and paste this, but I'm just going through this. I'm going through the motions just to reinforce what we're doing. And what we're doing is we're just saying, hey, let's find out the shared potential energy between 1 and 2, and then add it to the shared potential energy between 1 and 3, so on and so forth, just as I described earlier. Number 5, then, it's going to be exactly the same. In fact, this is what I'll do. Number 5 is UB is going to equal, everything's the same. Well, not quite. All right, so I guess I'll fight through it. Ready? It's minus G M1 times M2, which is just M squared. Now, here's something new. It's not D, it's D over 5. D over 5. That's the distance between 1 and 2. And then just follow suit. Plus a minus G M squared all over D over 5 root 2. So let me just show that here, making sure I'm not going too quickly here. So that's D over 5, which it is. I'm just double checking. This would be D over 5 times root 2. Okay. Back to the minutiae, plus a minus GM squared. I'm on U14. What's the distance between 1 and 4? It's D over 5. And now it's time for U23 plus a minus G M2 times M3. That's where I get that M squared. The distance between 2 and 3 is D over 5. plus the minus G M2 M4, which is another M times M. What's the distance between 2 and 4? That is also D over 5 times the root of 2 plus, last but not least, minus G M3 M4 over the distance between 3 and 4. Okay. So if I simplify this, number 6, UB equals minus GM squared all over D over 5 times exactly the same thing. This would be 1 plus 1 over root 2. Oops, sorry. 1 plus 1 over the root 2 plus 1 plus 1 plus 1 over root 2 plus 1. Okay, that's UB. So I'm good to go now. I have the total system potential energy for state A, the big square. This is what's going on with the big square. I have this amount of potential energy with the little square. And I'm going to do, they want the change. The question is, what is the change in gravitational potential energy? So I'm going to delta. Delta is always final minus initial. So step 7. Change in gravitational potential energy equals the final potential energy, which is B. I ended up at state B, minus A. So this gets surprisingly easy. All you need to do is take energy state B, which is right here, and subtract from that, subtract this. And this turns out to be a surprisingly easy calculation. It is now 221. So I will see you, oh, too small. See you at 2:30. And we will do more gravity. See you at 2:30 p.m. All right, if you refresh, you should see chapter 13, quiz 4. I'm just double checking on my side. Okay.
I'm still stuck on quiz 3.
Yeah. How so?
I'm not getting the right answer. And I have no idea what I'm doing wrong.
Here's what I did, and I can add some stoppage time, but this is how I made my life easier. Maybe it will appeal to you, maybe it won't, but this is I basically took this expression. Hang on a second. I took this expression. 1 plus, I took all of that. And whatever that equaled, I stuck it in calculator memory location A. And in fact, I think I still have it there. So when I add, for me, and I think it might be the same for all of us, I think, maybe not. But for me, it was 5.41 and some change. So it's just 5.41 and some change. All right, and then that's what I have here as well. This is also what I have in memory location A. So if I do UB minus UA, here's UB minus G M squared all over D over 5 times memory location A minus a minus G M squared over D times alpha memory location 5 minus G M squared over D So what does this equal? Here's common factors. Ready? G M squared, calculator memory location A, over D, that's a common factor. And then I'm just left with 1 minus 5. And this is what worked for me. Step 7, step 8, step 9. Okay. So that's a way that's how I try to make my life simpler. Let's go on to, and
Well, I'm doing that, but I'm getting the same answer that I've been getting.
What I tried, because I had the issue too when I crunched those numbers, I just did the GM squared over D, and then I did -4 minus 2 over root 2, and that gave me the right answer. So,
well, whatever. Yeah. I mean, here, I'll run these numbers. Let's see. So I have 6.67 E minus 11 times 0.01 times 0.01 times alpha A divided by 0.5 times -4. I get the right answer. So when I do this, exactly what I have here, this equals -2.889 E minus 13 joules, right? Yeah, joules. So you know what? Let me suggest the following. I can leave some time on the back end, but rather than talk about very operational math and calculator steps and order of operations, let me say that I'm confident you're going to be able to figure this out. So in the name of expediency, let's go on to quiz 4, 1, 2, 3. This is quiz 4. You should still be seeing quiz 4 now. Because I mean, full disclosure, I'm pretty sure you guys are going to be able to get yourself unstuck for those 1 or 2 of you. Well, I guess 1. Well, I don't know. Maybe no one's stuck at this point. This is another energy analysis problem. So energy analysis is kind of like I think of like energy analysis as like graduate school, and kinematics analysis is like high school, force analysis is undergraduate, energy analysis is graduate. So I always kind of think like that, just in terms of I guess level of sophistication, because energy analysis kind of subsumes kinematics and force analysis. But this is EAM. That's EAM. And here's what's going on. You have bowling ball A. I'll just use that term. You have bowling ball A, different size. I don't think bowling balls come in different sizes. Maybe they do. I know bowling balls come in different masses, but I think they all are kind of a uniform size, but maybe that's not true. However, sweeping that aside, bowling ball A and bowling ball B, or I'm sorry, bowling ball A and bowling ball C are fixed in place. Bowling ball B is moved. So you walk up to bowling ball B and you move bowling ball B from here to here. And you know that wouldn't happen naturally. If I let go of bowling ball B and I just looked at bowling ball B, if left to its own devices, would move towards bowling ball A. You know that's what would happen. That would be the natural response. How do I know that? 2 reasons. The mass of bowling ball A is greater than the mass of bowling ball C. Here's the mass of bowling ball A. Got it. There's the mass of bowling ball C. And as if that's not good enough, bowling ball B starts out closer to bowling ball A. And remember, we're dealing with an inverse square law. It's FG equals G M1 M2 all over R. So the gravitational force depends on the masses involved and the distances between the masses involved. So that's how I can put 2 and 2 together. And I know the only way bowling ball B is going to move to the right towards bowling ball C is if I do some work. So this is work. This is the work that you do. And I'm using the word you. This is the work that you do because it says how much work is done on the sphere by you? Okay, so you're the external force. All right, so let's do energy analysis. EAM energy analysis says the energy at state A plus the non-conservative work equals the energy at state B. And then you know what? Here's what I'm going to call state A. This might get a little bit messy. Here's state A. State A is bowling ball B on the left. So here, I'll do it like this. This is energy state A. There's bowling ball A, bowling ball C, and bowling ball B. I'm going to call this energy state A. The system with bowling ball B near A. Here's energy state B. Energy state B will look like this. It's bowling ball A and bowling ball C and bowling ball B that's now over here. All right, maybe not the simplest thing to look at, but maybe good enough. This is energy state B. Okay, so I'm going to remind myself, here's the baseline, because you still have to always worry about the baseline. The baseline here is the gravitational potential energy between two objects infinitely far apart is equal to 0. That's my baseline. All right, so let's see it. Energy state A. Could be some kinetic energy, could be some gravitational potential energy. Do I have non-conservative work? Yes. This is the work that you do. You are literally the external agent. You are grabbing hold, as mentioned, you are grabbing hold of bowling ball B and shoving it to the right. That wouldn't happen naturally. This is considered a non-conservative force, which means non-conservative force means it's path dependent. It depends on the path. And knowing what depends on the path, knowing what our path dependent versus path independent forces are is very important. Non-conservative force means non-conservative work. So this is not equal to 0. All right, so, and in fact, that's our dollar sign. So it's good that it works out that way. Energy state B, which is in that black loop. Energy state B is maybe some kinetic energy, maybe some gravitational potential energy. Okay, low-hanging fruit. The system starts out at rest and it ends up at rest. So in energy state A, everything is just sitting there static. So that's 0, that's 0. Energy state B, it's also static. So that's what I'm saying. Energy state A, everything is motionless. That's why there's no kinetic energy. At energy state B, everything is again motionless. That's why that equals 0. What's happening between A and B? It's the work you're doing. You're actually moving particle B from that left side to the right side. So step 3 is ready. I guess we have to do superposition. Here's my total gravitational potential energy at state A. Ready? It's U, A, B. So we're pairing up the thing. We're pairing up everything. So gravitational potential energy between A and B. You know what I better do? I better do this. It's UA between A and B. It's UA between B and C. And last but not least, it's UA between A and C. All right, that is my total amount of system potential energy for energy state A, plus the work that you do equals same thing on the right side. I have some potential energy between A and B. I'm just being like really careful with my subscripts. I have some gravitational potential energy between B and C. Again, referring to state B. And last but not least, I have some gravitational potential energy between A and C. Low-hanging fruit. There is one low-hanging fruit I can pick off. The distance between A and C doesn't change. So whatever this potential energy is, it's not equal to 0, but whatever it is on the left side for state A is the same as it is on the right side. So that they go away. All right, so number 4, we need to solve for the work that you do. The work that you do moving bowling ball B to the right, which is not what it wants to do naturally, is going to be UBAB plus UBBC minus UAAB minus UABC. And keep your eye peeled for mistakes. This is going to equal minus G MA MB. Now here's a big question. So I'm working on this term right here. I'm working on this term. Follow the subscripts minus G MA MB. Okay. What is the distance between A and B for energy state B? So it's right here. Let me clear the deck, clear the clutter. What is the distance between A? I'm just reading this here carefully. What is the distance between A and B for energy state B? Energy state B is that orange loop, my final state. The distance between A and B is L minus D. L minus D. The distance between A and B for this final state is right here between A and B for the orange state. That's it. This purple line. That purple line is equivalent to L minus D. Okay, so let's keep going. Plus a minus G MB MC. So for energy state B again, what's the distance between B and C? So now, again, I'm still looking at my orange loop. The distance between B and C is right here. Here's B, here's C, and that distance is D. Okay. 2 down, 2 to go, plus the minus GMA MB all over the distance between A and B for state A. Well, here's state A is that black loop. The distance between A and B in this black loop to begin with is right here. It's D. All right. That's the distance between A and B before I applied my force. So that distance is D. D plus a minus G MB MC all over the distance between B and C for energy state A. Energy state A, again, is that black loop. The distance between B and C for energy state A is right here. Here's B, here's C, and that's also L minus D. L minus D. All right, that's the answer. Let's pull out, let's simplify. A lot of simplification going on. Well, you know what I'm going to do? Here, I'll do with my numbers. My L is 24 centimeters. My D is 6. So 24 minus 6 is 18. So this is just going to be 0.18 meters. This is going to be 0.06 meters. this is going to be 0.06 meters, and this is going to be 0.18 meters. All right, and then the masses are all different, so I can't do anything with those. But well, all right, here's my simplification. Minus G. All right, minus G times MA, don't forget to convert from grams to kilograms, times MB, all over 0.18 meters, plus MB, MC, all over 0.06 meters, plus MA, MB, all over 0.06 meters, plus MB, MC, all over 0.18 meters. All right.
Aren't we subtracting the last two ones?
I think you're right. I think you're right. You're right. So plus, let's see. Yeah, you're right. I got to bring, when I bring these over here, so it would be a minus minus. So I'm going to do this. So that's a good catch. Very good catch. All right. So here and here. All right. So this would be plus, plus, and then this would be technically minus a minus. That's this is just how I like to do it. Okay. So this would be minus minus. You're right. Crisis averted. Minus, and I'm pulling in the minus G, so that better be okay. Good one. All right, let's run the numbers. Converting from grams to kilograms. I'm just going to do this. MA is 76 grams. MB is 11 grams. I guess I could have pulled out an MB. That was a common term. Forgot, or I didn't see it. MC is 0.022. So I could have pulled out an MB. Hmm. I've got to debug. I'm in a debug situation here. Minus G, 24.6. Okay. MPMC. Oh, there's my mistake. Okay. All right. And I get a positive result. I actually get positive 4.4022 and some change. No, 4.4022 exactly. E minus 13 joules. This is the answer to part A. This is the work that you do. And I would expect that to be positive because you're applying a rightward force and the object is moving to the right. Okay, part B. Part B says, do we have to go through this same horrible, well, it's not that bad, but do we have to go through the same amount of work to find the work done by gravity, by you and by the network? So by gravity, by F sub G. This is our dollar sign for part B. So you know what I'm going to lean on? I'm going to lean on the work kinetic energy theorem. 4, 5, 6, 7, 8. Here's the work kinetic energy theorem. Work, the net work done equals the change in kinetic energy. Okay, so I know the change in kinetic energy is 0. Why do I know that? Because final kinetic energy is the same as the initial kinetic energy. The final kinetic energy is equal to 0 because all 3 bowling balls are at rest in state B. In state A, all 3 bowling balls are also at rest. So there's no change in kinetic energy. So I can say, well, the net work done is equal to the work done by you plus the work done by gravity. Because remember, as you're pulling the bowling ball rightward, as you grab hold of this bowling ball and move it to the right, you're doing positive work, but gravity continues to act. Gravity still wants that bowling ball to move leftward toward bowling ball A. So that's doing some work. And in fact, that's doing negative work. This is the displacement. B is moving from here to here. This is X, but the gravitational force is still trying to go that way. So that's theta equals 180 degrees, and the cosine of 180 equals -1. And you're remembering work equals integral of F dx cos theta. All right, so there, step number 10 then, if that equals 0, there's no change in kinetic energy, then I can say the work done by you is going to be exactly equal to the negative work done by gravity. So that's why I have the same answer for part B as I did for part A, except a different sign, because the sum of the work is equal to 0. Okay. This is the answer to part B. Moving right along. Okay. Finish up that if you need another moment. I'll get the next quiz ready. Quiz 5. Quiz 5 is problem 39. 1, 2, 3, 4, 5. Okay. It's now 3:02. Okay. Chapter 13, quiz 5 is hopefully available, and equally hopefully it looks like this, a satellite. All right, so now this is our first orbital mechanics problem. Well, is it? Well, it kind of it is. You'll see. Orbital, it's not really orbit. It's an object that escapes an orbit. So here we have, what is the escape speed on a spherical asteroid with known properties? So let's draw a spherical asteroid. Here is my asteroid. Spherical. Okay. There's a probe. So a probe is sitting here on the surface of this asteroid. Let's say here, just for the sake of conversation. That's a probe. Think of it like a rock. You just think of this as a rock. That red dot is a rock. Did you know if you could throw this red rock fast enough, it would actually leave the orbit of this asteroid, and that's called escape velocity. Escape velocity is the launch velocity or the takeoff velocity or the initial kinetic energy needed by an object to escape the gravitational pull of whatever planet or asteroid or black hole or galaxy that it's trying to flee from. All right, so you walk up to this rock. Let's just think of it as a rock. You walk up to the, well, they call it particle, but let's just refer to it as a rock. All right, so you're going to give this rock an initial velocity. All right, so here is the initial velocity you're giving to the rock, right? Like that. Okay, so it's just like you throw it. And if you want to think in more grandiose terms, this is a rocket at Cape Canaveral sitting on a launch pad that's going to be basically tossed up into orbit by huge engines. So this is, I'm going to call this velocity at energy state A. Okay, what else? Before I move on, the radius of this asteroid is 700,000 kilometers. So I'm going to note that this radius, right now I'll just refer to it as the radius of the asteroid. Okay. All right. And I'm just going to draw that same radius line here. This is also the radius of the asteroid. This is the center of the asteroid right here. Okay. So when you throw this rock outward, radially outward with respect to this asteroid, and this asteroid is a sphere, so this would be the center of mass. The center of mass is the point at which we can think of all of the object's mass being concentrated. That's the center of mass. I'm going to throw this rock so hard that it leaves the orbit. It leaves the influence of the asteroid. So I'm going to call this M. This will be what I will call M subscript. Well, they're calling it a particle, so I'll go to particle. That's the mass of the particle. The mass of this asteroid is M subscript A, mass of the asteroid. I throw this particle with so much initial velocity that this particle ends up at infinity. So let's draw that. This particle ends up at infinity, right? There, that's infinity. I found infinity. That is infinity. Okay, so here's the particle at infinity. Okay, at infinity, if I give it enough initial velocity, all of that initial kinetic energy gets converted into gravitational potential energy. So, and I used up all my kinetic energy. So I'm going to say V at energy state B equals 0 because I used up all kinetic energy used up. All the kinetic energy is converted into gravitational potential energy. Also at energy state B, I can say this. I have the greatest, I'm sitting at, this particle is sitting here at infinity, which means I have a gravitational potential energy of 0 joules. So check that out. This is what it means to escape the velocity of a central object or the object that you're initially bound to. It means if you've escaped, if you manage to escape, you end up with the maximum possible gravitational potential energy. And 0 is the maximum possible gravitational potential energy. Remember, I graphed this in Desmos and it was looking like that. 0 is the greatest amount of gravitational potential energy. As mentioned, I've used up all of my kinetic energy. All of that kinetic energy got converted into gravitational potential energy. So that's energy state B. For energy state A, here's my initial VA equals V escape. That's my escape velocity. That's my $sign. And I do have some initial gravitational potential energy. My gravitational potential energy at A is minus G MA, which is mass of, well, I'll do MP, mass of the particle times mass of the asteroid all over the distance between them, RA. Okay, that's it. So now it's EAM to the rescue. EAM says the following. There's no springs involved and there's no rotational kinetic energy. There's translational kinetic energy. I might have some, well, energy at A. There are, in this case, there are no non-conservative forces. There's no external force adding or stealing energy. So I can quickly say, well, at energy state A, I could have some kinetic energy. I might have some gravitational potential energy. There's no non-conservative work. And at B, I might have some kinetic energy and some gravitational potential energy. Low-hanging fruit. At B, all of my kinetic energy got used up because I escaped the influence of the asteroid. At B, my particle attained the maximum amount of gravitational potential energy, which is 0. So I'm left with now kinetic energy at for energy state A equals minus UA. So you know what that means. Energy state A kinetic energy is 1/2 mVA squared. That's the kinetic energy for state A equals the minus of a minus G MA, or I guess I call it MP MA over the distance between the particle and the asteroid, which is RA. And again, you might think, wait a minute, Chris, isn't the distance between the particle and asteroid 0? No, we're referencing center of mass values. So let's solve for VA. VA, which again is the escape velocity. Go ahead and get yourself, oh, I forgot. This is 1/2 mv squared. Should this be 1/2 m subscript p? Is that 1/2 mp VA squared, or is it 1/2 MA times VA squared? And we have to go with P because P is the object. The particle is the object being ejected away from the asteroid. So there's some more low-hanging fruit. MP cancels here. So let's get a number. Let's get a number for the escape velocity. Oh, trouble. Stuck. Stuck. You know why I'm stuck? I don't know MA. MA equals, I don't know the mass of the asteroid. So there's got to be a way out of this. I guess I'll read the question. I know the radius of the asteroid, and this is the one piece of data I haven't tapped into. I do know. Yep.
Sorry, one more issue that you come across. If you're solving if you're solving for VA, you have to take the root of whatever's on the right side to get VA alone by itself, right?
Whatever you need to do. Yeah, you do the math.
But I guess my question is, are you going to come, like, you can't take the root of a negative number, right?
But it's negative of a negative.
Oh, I see. I got you.
That's how I do it. I mean, you probably would just automatically call that a positive. This is just my, this is my thing. That's just my thing. So
I got, okay.
That's good. Good that you spoke up. All right. So I don't know MA. So how can I tap into this? You know what this is saying? Number 5, on Earth. So G for Earth, for E for Earth. G on Earth is 9.8 meters per second squared. According to this problem, G for this asteroid equals, for my number is 0.958 meters per second squared. All right, so this obviously, this G value depends on basically mass and size. You can't just look at it. You can't say, well, the Earth is more massive than the asteroid. That's not sufficient. You have to look at the combination of mass and size. So how do I exploit this? I'm going to remember what weight is. I'm going to remember that we all know that weight equals mg. Okay, we've used that countless times. All right, so specifically for the particle, the weight of that particle is the mass of the particle times whatever that G value is on the asteroid. And you know what weight is? Weight is basically just the gravitational pull. Like your weight, my weight right now is the gravitational pull of the Earth on me, which is the same as the gravitational pull of me on the Earth. So this is specifically what we call weight. And more generally, what is weight? Weight is a gravitational attraction. So here's the equivalent expression for weight. Ready? G MP MA all over RA squared. So these are equivalent terms. All right. This is an expression for weight. This is an expression for weight. And I'm going to solve for something. I need to find MA. So you know what I'm going to do? Here's some low-hanging fruit. MP cancels with MP. So I'm just going to leave it as GMA unless I But right now I can see this GMA, big G times mass of that asteroid equals little g times RA squared. And I can use that. So this is a giant sigh of relief. I'm going to go back to number 3. So here's my new number 3. I've got 1/2 VA squared, which is my escape velocity, equals GMA. Here's GMA. Ready? GA times RA squared all over RA. And you can see yet more low-hanging fruit. One of those cancels with that one. So I think it's safe to solve for the escape velocity now. Let's do that. Okay. This is the magical escape velocity. So if you can throw this object with that velocity, it will never come back. It will slow down, but it's never going to come back, theoretically speaking. This is I better do it like that. Okay, that's the answer to part A. That's the answer to part A. I'm going to make a copy of this. This seems handy. Okay, that's our escape velocity. Now, interesting. There is, I don't know how current this conversation is, but at one point, I know engineers and NASA people and jet propulsion people, they were talking about literally catapulting or firing, like using ballistics or like a rail gun. Rail gun is not a ballistic device, but here's the thinking. If you can if you have a strong enough slingshot, you could literally slingshot an object from the Earth into orbit into orbit. Because right now what happens when an object leaves the surface of the Earth, the rocket engine continues to fire. So the rocket engine is a source of tremendous non-conservative work. And getting an object getting an object off the surface of the Earth is a major challenge, mostly because it's expensive. So what's the ULA rocket? United Launch Alliance, like here. I mean, they're spectacular to look at. This is, I guess, what I'm thinking of, one of them. But this is why the space exploration, anything to do with space, is tremendously expensive. Right here, this picture right here, because escaping the clutches of Earth's gravity requires a lot of energy. So not only does this rocket have a lot of energy on the launch pad, but it continues to receive investments of energy during the course of its flight. And it doesn't escape the Earth's gravity, but it's pulling away. It's basically fighting the Earth's gravity, which is why this is a big deal. It's really expensive, really complicated. So the thinking is, what if we just take a gigantic cannon and shoot an object into orbit? And I know, for all I know, this might be, that might be an abandoned idea, or it might be actively under development. I can't remember, but that's what we're doing here. Here, we've basically chucked it with enough kinetic energy so that it left the building, it left the influence of this asteroid. Part B says, what if you give it less? What if you don't give it enough initial launch velocity? So I'm looking at, I know for me, my escape velocity is 1,100 and some changes, almost 1,200 meters per second. For part B, it says you're not going to give it 1,100 or 1,200 meters per second. You're going to give it something less. So I know, just looking at B, looking at the number I have for B and looking at my result for A, I'm not going to leave. I'm not going to leave the influence of this asteroid. So I'm going to repurpose my drawing here. I launch from A. Everything at state A can remain the same. However, at state B, I don't make it to infinity. So I think, well, you know what, to be honest, everything's going to kind of stay the same, except my gravitational potential energy at B does not make it to 0. 0 is the biggest number possible. It makes it to minus G. I better move this. Minus G, 1 second. Okay, so I don't make it to infinity, but I do make it to minus G, mass of the particle, mass of the asteroid, all over that distance. What is this distance? You know what distance I have to deal with? I actually have to deal with this center to center distance. From there, that blue line. This blue line is what I have to deal with. So this blue line distance is going to be, I guess I'll just call it Rx. This from here to here, that's Rx. Some distance, maybe I'll just call it X. And then here to here, this is Ra. So my denominator here would be X plus Ra. All right. And now it should be business as usual. Oh, except VB. Yeah, that's fine. Everything I think remains intact. I made this update to the gravitational potential energy at B, which is not 0. It's something smaller in magnitude than 0. And that would be some negative number. All right, so then let's just do energy analysis. Well, okay. So it's going to, this particle is going to reach a peak altitude above the surface of the asteroid, and then it will slow to a stop, and then it will come crashing back. Okay, so number 2, energy state 8, kinetic energy plus gravitational potential energy. There's no non-conservative work because the rockets aren't firing. The rockets would be a source of energy addition, not loss. And then at B, KB, that does equal to 0, plus UB. All right, so this is equal to 0 because my particle slows to a stop because I didn't, well, either way, it would slow to a stop. It either makes it to infinity. At infinity, it slows to a stop. At something less than infinity, it still slows to a stop. I have 1/2 MP VA squared. I got to be really thoughtful about these subscripts. This is the kinetic energy of the particle plus a minus G mass of the particle, mass of the asteroid, all over, and this is energy state A, so this would be Ra. Yes, equals minus G mass of the particle, mass of the asteroid, all over X plus Ra. X plus Ra. And we're solving for X. So I guess the first thing I'm going to do is I'm going to multiply through by 2. If I multiply through by 2, mass of the particle VA squared, which I know I know the velocity. Oh, low-hanging fruit. Let me do low-hanging fruit first. MPs cancel. So again, we're so focused on MP, and yet MP actually plays no role. MP, MP, MP. Multiply through by 2. If I multiply through by 2, I've got VA squared minus 2G MA. And I actually know what, I know I'm remembering this. This could come in handy. All over RA. And I'm still multiplying by 2 equals minus 2 MA all over X plus RA. Let's do a little inventory. Do you know the value of VA squared? Yes. Well, VA is 990 meters per second. Do you know the value of MA? No, you don't, but you do know that G times MA is equal to GA RA squared, and you can see one of those numerator RAs cancels with the denominator RA. And I forgot the G over here, so let me fix the typo. Minus 2 times G MA. So same story here. This is going to be equal to G RA squared. RA squared for me, 700 kilometers equals 700,000 meters, or you could just say 7E5 meters. All right, so we know everything here except for the dollar sign. So you should be good to go. Let me do a time check here. It is 3:28. See you at 3:38 p.m. for more orbital dynamics. Okay. I think this might be the last quiz for today, just because we have to break into a new topic to do the next quizzes, and I don't think time will allow that. Let's do chapter 13, quiz 6, which is an energy analysis problem. All right, I have 3 particles, MA, MB, and MC. M, B, and C are basically stuck in place. MB and MC are stuck in place. Here's B. Here's C. A can move, though. It says particle A can move. So I can move A down to that line, which I guess this is a perpendicular bisector, or I can move A all the way up to infinity. Okay, so A is slidable. And once you slide it in position, you basically anchor it into that position. All right, and we have a graph. So once again, I'm going to look for the obvious from my graph. And I can see that this seems to be a crispy point. This y-intercept seems to be a crispy point. And again, they give us an asymptotic value. So whatever this asymptote is, it's here, and it's stated as negative 2.7 times 10 to the minus 11th joules. That's the asymptotic value. All right, so part A, here's part A. Part A of this problem is showing how particle A can be moved along the y-axis from an infinite distance, as mentioned, all the way to the origin. The origin lies at the midpoint of B and C, which have identical masses. So note, MB equals MC. And let's just, okay, well, let's leave it like that. MB and MC have identical masses, and the y-axis is a perpendicular bisector between them. Distance D is known. So we know this distance right here. This is known. This is known. Part B shows the graph, and this is where I have to read through a bunch of times. Part B shows the potential energy. This is the potential energy of the three particle system as a function of the position of A. So that's chock full of meaning for me, because we are talking about system energy, and it's the system energy as a function of particles A's position. So that's why I'm being, because for me, I just get, sometimes I don't see, what is this graph? What is this graph showing exactly? That's why I keep spending a lot of time on that statement. The curve actually extends rightward and approaches an asymptote of negative 2.7 e minus 11 as y goes to infinity. What's the mass of all these particles? Particle of MB, MC, and MA. So we got to find out the mass of all these particles. So I guess I'm just going to say, number one, let's look at what happens when mass of A, when particle A is at y equals 0. All right, so let's look at that situation. When particle A is at y equals 0, it's sitting right here, right at y equals 0. Okay, so at y equals 0, I have this much system potential energy, whatever that number is. I got to figure out what that number is. Let's see. This is how many boxes between major tick marks? 1 box, 2, 3, 4, 5. All right, so this would be like 2.0, 2, 4, 6, 8, 10. That's 3.0, 3.2, 3.4, 3.5. So I think this number is negative 3.5 times 10 to the minus 10th. I think I'm doing that right. That number right here is, let me do it like this. All right, so I'm seeing this as negative 3.5 times 10 to the minus 10th joules. And I just want to sanity check myself on that. All right, because, all right, this is negative 2, negative 2.2, negative 2.4, negative 2.6, negative 2.8, negative 3, negative 3.2, negative 3.4, negative 3.5. I think I'm halfway between negative 3.4, negative 3.6. All right, so there. When mass A is at y equals 0, meaning it's sitting right on that line along with B and C, what's happening? Let's do the total system potential energy. I'll call this energy state A. So this is energy state A. So I have the total potential energy at energy state A equals U AB plus U AC plus U BC. Okay. So again, I'm just saying there's A and B, got it. Here's A and C, I got it. And here's B and C. Okay. Let's develop that before we move on to something else. Maybe we don't have to, because the dollar sign's living here somewhere. All right. So, all right. I have negative 3.5 times 10 to the minus 10th joules equals UAB. So it'd be minus G, mass of A, mass of B, over the distance between A and B. Got it? Plus a minus G, MA, MC, all over the distance between A and C. And last but not least, minus G, MB, MC over the separation between B and C. Let's see some simplifications. What can we do here before we just pay the price? Let's see. Well, MA and MB. MB equals MC. So you know what I'm going to do? I'm just going to call this M. I'm going to call this, and I'll say MB equals MC equals M. So that's M. This is M. And this is M squared. Okay. Okay. What else can I do? What is the distance between A and B? When y equals 0, the distance between A and B is going to be equal to big D. When y equals 0, the distance between A and C also equals big D. And when y equals 0, when A is at y equals 0, the distance between B and C equals 2D. Okay, let's do the same thing. Well, here, maybe I'll just give it one little update. Number 4, I'm left with negative 3.5 times 10 to the minus 10th joules equals minus GMA times M all over D minus GMA M all over D minus G M squared all over 2D. All right, so I have two dollar signs here. This is MA is a dollar sign. So is M. And I know whatever the value of M is, that's the value for B and C. I can't solve this yet, but something tells me I'm going to be able to use this. I need another equation. I have two unknowns and only one equation. So my second equation is going to come from energy state B. Energy state B. Energy state B is when mass A goes off to infinity. When mass A goes off to infinity, here's what I have. I have the total system potential energy, gravitational potential energy at B. I'm just going to do the same tedious stuff. AB plus AC plus BC. Okay, let's run with this. And this equals negative 2.7 E minus 11 joules equals UAB minus G MA MB. And let me do this right now. MA MB. What is the distance between A and B when A is at infinity? It's infinity. So that goes to 0. Minus G MA MC over the distance between A and C. The distance between A and C when A is off at infinity is also infinity. So that goes to 0. Minus G MB, which is M, times MC, which is M. So that's minus GM squared. What's the distance between B and C? It's still 2D. Okay, so I think we're going to be good to go. Yeah. All right. So from number 8, find M from number 7, and then use M to find MA in number 4. And I think that's the game plan. So we're getting pretty well practiced with dealing with gravitational potential energy for a system of particles. This is kind of similar to problems we've done before. So you know what? That will be good. So I'm going to do the unthinkable. We're going to end. Before I leave you guys, this is quiz 6. Does anyone need, let's talk about stoppage time. Does anyone need an extension for any one of today's quizzes 1 through 5? Any shout outs?
Just 5.
Yeah.
5?
Yeah, just 5. Yep.
Quiz
Same.
5. Let's see, it's about 4 o'clock. I'll make it available till 5 p.m. All right. So if there are no more requests for extensions, I will extend quiz 5 until 5 p.m. And we'll see you guys Tuesday at 1 o'clock for an exciting do-it-yourself solar system activity. All right, you guys, take care. Until Thursday, I should say. Today's Tuesday. Until Thursday. We'll see you on Thursday.